Okay, Simon, you're on.
Okay. Well, good morning or good afternoon, good evening, everybody. Welcome to SETILive. I'm Simon Steele, Director of Education and Outreach at the SETI Institute, and that's where I'm located at this moment. I snuck into the office, even though we're in lockdown. And speaking today to Ed Liu. Ed is a physicist, a former astronaut, and also co-founder of the B612 Foundation, and we'll find out a little bit more about that. But the reason we're talking today is it's Asteroid Day. So welcome, Ed. Happy Asteroid Day. And can you tell us a little bit about why we are celebrating asteroids on this day?
Thank you, Simon. It is an interesting day. Because today, June 30th, is the anniversary of an event that happened in 1908, where a small asteroid of about 45 meters across actually hit the Earth over Siberia, over an area known as Tunguska. It sounds like a small rock, 45 meters, the size of a building, for instance. But a rock moving at that kind of speed, and here we're talking like Mach 100 or so, actually exploded in the atmosphere. It was going so fast, hitting the atmosphere is like hitting concrete. It exploded with the force of about 700, with the energy of about 700 times the bomb dropped over Hiroshima. So it destroyed an area roughly the size of metropolitan Los Angeles, and flattened the trees over hundreds of square miles. And so it's an interesting day. It's a reminder that the solar system is populated by many, many bodies, most of which are asteroids, and sometimes they hit the Earth.
Now, fortunately, that came down in a very population-less region of Russia. Yeah. I suppose statistically, if
just some reindeer and stuff,
it'll come down in the ocean or in Siberia.
Yeah.
But there's some very interesting, if you look at some of the images of the first explorers going there, it's quite amazing, isn't it? The trees toppled down and everything.
Yeah, it was many years until the explorers could get out there. It was so remote. And when they got out there, they found that these massive trees, and this is a very, very remote forest. These are huge trees, were blown down in a radial pattern outwards from the center of the blast, over hundreds of square miles.
That's fortunately, we'll talk more about the risks involved or potential risks coming up. But welcome everybody who's watching, who's listening. As usual, if you're regulars, please do let us know where you are watching from. We've already have a viewer from Uruguay. We have somebody from, I thought it was going to be Russian, St. Petersburg, but it's St. Petersburg, Florida. So that's almost the same thing. And of course, if you do have any questions for Ed, please do write in, and those questions will be passed on to me, and I will bombard Ed with questions, and the tougher the better, Ed, don't you think?
Absolutely. Those are the fun questions.
Yes, fun questions, definitely. So Asteroid Day, this happened in 1908 in Siberia. What is the significance to us today of that event and the celebration, if you like, of Asteroid Day?
Well, it's a reminder that that the majority of the bodies in our solar system are currently untracked, undiscovered and untracked. Most of the worlds in our solar system, 99% of the ones larger than the Tunguska, we have no idea where they are. Okay, they're orbiting the sun, but we have not yet tracked them. So we actually would not have warning of another event like this today, until, of course, big flash in the sky and potentially bad things happening. But one of the points that we've been making is that asteroids are very, very interesting. They're not just something to be feared. Of course, we know about major asteroid impacts that, like, for instance, killed off the dinosaurs, or throughout world history, there have been many asteroid impacts. But you can also think of them again as sort of undiscovered worlds. So that means science. That means understanding the formation. If we learn about asteroids, we can understand the formation and evolution of our solar system and of planet Earth. The record of that story is written in both their composition and in their orbits, in the distribution of orbits of these things. Also, given that it's the great majority of the objects in our solar system, they are part of the landscape. destinations to go to. They are places where there might someday be resources, but they're certainly part of any map of the solar system that you would eventually make when humans do move outwards in the solar system. Well, asteroids are going to be very, very prominent. In fact, like I said, most of the objects. And then, of course, we don't want to get hit by them. So there's a whole lot of reasons why asteroids are actually quite important.
Yeah. I suppose it's like, yeah, it's important to study tigers, but you really don't want to sort of be wandering around the house with them. So,
well, it's a little bit different. In some cases, you do want to be around the asteroids, right? Because they are places to go to. So they're not just threats.
Yeah, yeah. So there's a lot of asteroids, of course, are in what's called the asteroid belt between Mars and Jupiter. And then, of course, there's the Kuiper belt, which is the band of sort of more icy comet-like rocks out beyond Neptune. But there are also these other objects, what are called near-Earth objects, NEOs, which are obviously moving in closer than Mars and coming very close to us, and these are the ones we're worried about. It doesn't the ones in the asteroid belt are fine. We don't need to worry. We can study them at our leisure. But tell us more about where these ones, these near-Earth asteroids, we think what they're coming from and how they're moving.
Yeah, near-Earth asteroids, as you say, are near Earth, so that means they orbit the sun at distances kind of similar to Earth, which is why they can sometimes hit the Earth. Now they come out of the asteroid belt to begin with, so as the great majority of asteroids do orbit between Mars and Jupiter, and occasionally one of their orbits gets perturbed, usually by coming too close to Jupiter in most cases, but sometimes Mars, and at which point the gravity can of say Jupiter as it comes close by can change the orbit. This is similar to what we do with spacecraft when we call them gravitational swing bys, when we send a spacecraft close to a planet to pick up energy or to lose energy to change its orbit greatly. And that change in the orbit can send them to a different orbit, which is actually closer to the sun near us. And that's the source of the near-Earth asteroid.
So Jupiter, especially Jupiter, I've heard it referred to as the vacuum cleaner of the solar system. It gobbles these things up. So it's good to have a Jupiter around in some ways.
Well, it does gobble them up, but in many cases it just changes their orbits. Doesn't actually. It's sort of like a poor vacuum cleaner in some sense, because it doesn't, put it into the bag. It just stirs them around.
Yeah, I've got one of those at home. I know exactly what you mean by that.
Ours does that too on occasion.
So we got a lot more people. Let me just run down this list of, it's basically a list of places on Earth. Wales, Carmarthenshire, Cornwall, Vancouver, Germany, they're coming too fast for me to read now. It's a test of my eyesight. Norway, Belgium, France, Sweden, Finland.
Wow, this is a testament to the interest that SETI and I'm hoping asteroids also are, engender in the general public.
Yeah, absolutely. And Australia, some people are up at very odd hours as well. Yorkshire, Scotland, Minnesota, Washington State, Morocco, and Italy. So a wonderful list of viewers. And some questions are coming in, and I'll ask those in a minute. So I'm looking at your shirt. Very nice polo shirt there with B612 on it. Could you say a little bit about and where do you get the shirts? Can you say a little bit about your foundation? And first of all, the name is interesting, isn't it? And tell us a little bit about what you're doing.
Yeah, our work is dedicated towards the last aspect of asteroids, preventing them from hitting the Earth. And we got the name years ago when we started this organization. It's been almost 20 years now, from the asteroid home of the Little Prince. And if any of you have read that book, you'll know that the Little Prince came from asteroid B612. And we like the message of the book was essentially that sometimes the important things are things that adults don't recognize, because they're too busy looking down, looking at their everyday lives, counting their money, or who knows what, the various characters that the Little Prince meets. But sometimes it's important to look up. And that is really our message, that human beings do have the capacity to look up, to change the solar system if needed, to protect ourselves. I mean, if you think about what we're actually talking about doing, it is finding and tracking asteroids and knowing decades in advance when they're going to hit, if one is going to hit the Earth, and they do. But if you have decades of notice, we can fairly easily prevent an asteroid from hitting the Earth. That's actually the easy part. The hard part is knowing that a particular asteroid is going to hit the Earth decades ahead of time, and that's really what we've dedicated the B612 Foundation and our Asteroid Institute to doing.
Okay, okay. We got a couple of questions here. Actually, maybe this is an important one from Laurie. What are asteroids made of? What are we talking about when we talk about an asteroid?
Well, most of the asteroids they're parts of leftover chunks of planetary stuff from the early part of the solar system. When I say planetary stuff, look outside. Most of the Earth is rocky, right? The central core of the Earth is metallic. And if you look at asteroids, most of them are rocky, basically rocks or, small conglomerations of rocks. Some of them are made out of iron or nickel, kind of like the central part of a failed planet. And so think rocks in space, some of them large.
Mm-hmm. Yeah. So a question from Night Owl. Hi, Night Owl. I imagine you're somewhere where it's dark at the moment. Are all asteroids smaller than 20 meters harmless? Is there a cutoff point where these things just, burn up and don't actually get down to the surface?
Well, there is no hard cutoff. And the 20 meters that you mentioned is actually a significant number because that's roughly the size. Our best guess is 19 meters. Of the asteroid that hit in Chelyabinsk in 2013, just a few years ago.
Yeah.
Now that one had explosive energy about 30 times the bomb dropped over Hiroshima. So still a pretty large explosion, but we were lucky in that case because that asteroid was going over the top of Chelyabinsk. It wasn't headed at it. It was going almost parallel to the ground, just a few degrees off over the top of it. And that meant the vast majority of its energy did not hit the city. It went over the top of the city.
Yeah. Yeah.
And that's why we didn't see, 500,000 casualties that day. We only saw a couple of thousand people in the hospital and, a few 100,000 windows. Essentially every window in the city was broken. But that was very lucky. So that was about a 20-meter sized asteroid. Now, that tells us that a 20-meter sized asteroid could actually cause great damage on the ground. It depends. It depends upon how fast that asteroid is moving, and there is a bit of a range, perhaps a factor of 2 in the speed of asteroids. There is quite a bit of range in what they're made of, in the sense that you can have harder rocks, denser rocks, or even chunks of iron, as we mentioned before. So it depends. So there isn't a hard cutoff as to when you're going to get damage on the ground, but we know that Tunguska, which was 45 meters roughly in size, that obliterated an enormous area on the ground. That causes damage on the ground no matter what. Mm-hmm. So somewhere between there is where you transition from, maybe it's not so bad to it's really, really bad.
Yeah, yeah. And as you say, there's so many other factors involved, the angle of strike and the density and how sort of
unit. So there isn't a single answer to that question. Yeah. But a good question though.
Yeah. We got somebody listening in from Bengaluru in India, Sao Paulo, South Wales, Hereford in England, Dayton, Ohio, Nottinghamshire, Connecticut, Newcastle upon Tyne, and Gothenburg in Sweden. Here's a question on statistical hits. No name attached to this question. How many 20 to 30 meter asteroids hit the Earth per century, per week? How much of this stuff is raining down on us as we orbit the sun?
Well, an asteroid the size of the one, let's just pick the Chelyabinsk case, the 20-meter case. So that size or larger, roughly every few decades hits the Earth. But most of the Earth's unpopulated. That one just happened to come raining over the city when a lot of people had video cameras. So,
dash cams, yes.
Yeah, exactly.
Yeah. Yeah.
Now, I should mention that these near-Earth asteroids are quite a bit less common than the main belt asteroids, because most of them are still in the main belt. Mm-hmm. But it's interesting. Actually, last night, I did want to bring this up. An interesting project done through SETI is the Unistellar eVscope. Mm-hmm. And Frank Marches from SETI brought one over to our house last night. My son and I went outside, and this is a rather amazing telescope, in that we were actually able to use it to actually observe a main belt asteroid moving in the sky. And, this asteroid happened to be around, I think it was slightly under 10 kilometers in size, but out in the asteroid belt. So, this thing is, of order 100 million miles from the Earth or more. And yet we could see it, out here. And I live in a sort of suburban area. There's street lights outside. There was a moon outside. So, like right here in the middle of the city, right close to San Jose, California, we could actually see that. It was actually quite amazing. And as we waited some time, you could see that dot was moving.
Mm-hmm. Mm-hmm.
So it was really neat. It's really neat to be able to see it, yourself.
Yeah, that is amazing. And of course, Frank, who's our senior planetary astronomer at the SETI Institute, also has talked a lot about his telescope technology and the ability that has to give amateurs or citizen scientists the chance to make scientific observations. I suppose how asteroid tracking and things like that. How much can amateurs get involved in this?
Well, it's certainly things that are, if you have the ability to know where to point, and that's one of the beauties of the system, the Unistellar system, is that it's not just telescopes. It is a data system behind it, an app in which you can, receive real-time information, and that's what allows you to point these things, because these trajectories are changing. So I think that's really what's very, very interesting about these particular telescopes. But amateurs can get involved in refining the orbits of asteroids that are known to exist. They can even get involved in discovering asteroids that, for the first time, ones that come near the Earth. And I think that's a really amazing thing, that someone who is a professional astronomer can actually go out there and do that. Yeah. Now, that's not to say that is a large number of near-Earth asteroids, because there are enormous telescopes out there searching for asteroids.
Yeah.
And by enormous, I mean really enormous. And so, nothing that a single person can buy really can compete against those things. Absolutely. But the additional observations can help refine orbits. And I think that's a really neat thing to be able to say you've done.
Cool. And I know Frank is listening. Hi, Frank. And maybe you can post, if you recorded the observations you made last night of this asteroid, we can pop that onto Facebook so people can see these observations, and that'll be really cool. And obviously you can find out more about this work and Frank's Unistellar scope on our SETI Institute website. So do take a look at that.
Yeah, we also did something fun last night, which was knowing ahead of time the orbits of the SpaceX Starling satellites. We were able to point the telescope and wait for it. We observed two of these satellites, and right on schedule, right through the screen comes a SpaceX Starling, clearly visible, and it's very neat to be able to see that.
That is cool. Actually, there's a question from Zila B93, human, possibly Android, I'm not sure with that name. Are the Starling satellites going to cause issues for astronomy in general, and maybe for hunting these tiny point sources especially?
I think this is something that is still not quite fully known yet. These SpaceX people are working with the scientists at the Large Synoptic Survey Telescope, which is going to be far and away the world's largest asteroid hunting telescope, which is coming online in about a year and a half in Chile. It's a good fraction of $1 billion telescope. It's an 8.5 meter diameter main lens and or main mirror, and those scientists have been working with SpaceX on this. Now, in most cases, those satellites they're not really an issue unless they are in the sunlight and the observer is in the dark, which means sort of in the sort of half-hour, 45-minute period, dawn and dusk. That's when you get interference from debris or satellites orbiting the Earth. That is not the majority of the observing time. But that being said, LSST takes such wide field of view images of the sky that you do stand a decent chance of having something going through there. Keep in mind, though, that there are 250,000 objects larger than 2 centimeters orbiting the Earth. There are about 10,000 currently larger than 10 centimeters orbiting the Earth. Okay, so Starling satellites are not the majority of stuff out there. In fact, already there is an issue.
There's plenty of stuff up there.
Yeah, there is
without
plenty of
picking on
stuff
the
up there.
Starling system.
Yes.
Okay. And you mentioned LSST, which is an optical telescope. The question from Ernesto, do asteroids have a radar signature, or do they have to be detected in the optical? What different methods of detecting these? We've talked about a couple of them.
Yeah, asteroids do reflect radar, so you can track them with radar. Most of the asteroids are tracked optically. You can also track them in the infrared. That's sometimes easier because the background sky is less bright in infrared, and asteroids tend to be warmer than the background sky. Radar has one great advantage, which is that you can tell the distance very, very accurately. And that allows you to fit, in general, a much better orbit. And it's all about, the whole game of the game isn't saying I discovered an asteroid, it's saying I tracked an asteroid. You need to know where it's going. So it's all about the computation of the orbit. That's the important thing. So radar makes that much easier. The big problem is that radar cannot see something that's very far away from Earth in general, because radars are cursed by what is known as the 1/r to the 4th law, which means that the signal strength you get back from bouncing off that drops off as the distance to the asteroid to the 4th power, which is horrible. It's a very fast dropping off thing. It means anything more than about 1 million miles away, you don't really have much of a hope of getting radar off of it. So that means any asteroid that you track with radar has to get extraordinarily close to the Earth. And that is not true of the vast majority of asteroids at any given time. So it's not great for discovering asteroids. In fact, it's absolutely horrendous for discovering asteroids. Radar is very, very good for refining the orbit of an asteroid that you already know where it is, roughly, and it's coming very close to the Earth. Very small fraction of asteroids, but very useful in those cases.
So it's not an early detection tool, it's much more of a characterization and fine-tuning.
It's an orbit refinement tool.
Yeah,
it's an orbit refinement tool, but that can be very, very important.
Mm-hmm. Yeah.
Because, say, for instance, we have an asteroid like Apophis, which was discovered in 2004. At one time, we thought it was going to hit the Earth in 2029. That's because it, in fact, is coming very, very, very close to Earth in 2029. It's going to miss the Earth by just 16,000 miles. And, so how do I make that statement a decade in advance, right? This is 10 years from now, 9 years from now. The reason is because we actually can calculate that. We know that orbit so well. Why do we know the orbit so well? Because about 10 years ago, it passed close to the Earth, and we were able to put radar on it. And that radar tracking allowed us to reduce the uncertainty in our orbit well enough that we could rule out that it was going to hit the Earth in 2029. In fact, we kind of know the distance that it's going to pass the Earth by to within about 1 kilometer or so.
Yeah. We've had, of course, a few questions from people asking, you've detected this thing now. It's not going to miss us by 16,000 miles. 2020 is bad enough. Nothing's heading our way just yet, thank goodness. But if, say, something, if that orbit was refined to suggest, a likelihood of impact, what first of all would B612's involvement in that analysis be, and what can we do, or what is planning to be done about that? Okay,
so let's set this side into two problems. One, which is knowing that it's an issue and knowing that we do have an asteroid which might hit the Earth, and then what you do about it. Okay, so the knowing, again, the hard part is the first part. And the analogy I'm going to give is a bit like hurricanes. So if anybody here has ever lived on an area where there are hurricanes, the Gulf Coast of the United States, Florida, places like that, you're familiar with something called hurricane tracking codes. And when a hurricane is headed for the coast, a week or so away, they say, here are the range of possibilities where this hurricane could go. And it'll be a cone which spreads out in time. And let's say you live in Houston. You might say, oh, okay, well, according to this cone of this particular hurricane, it's going to hit anywhere from where I am to 200 miles this way to 200 miles this way. Makes a big difference, right? I could have really just like 20-mile-an-hour winds, or I could have 120-mile-an-hour winds and blowing down all the houses, right? Big difference. I could be in the sunlight and not even know this thing goes by if it's 200 miles away, or the other way around. So you follow these cones, and as you get closer to the landfall, the cone narrows down and you begin to get a much better idea of where it's going to go. The same thing happens for asteroids. So what is going to happen is that we are going to find an asteroid. We're going to know that it's coming close, but we won't know, for instance, even which side of the Earth it's going to be on, but it has a chance of hitting the Earth because the probability area of that cone extends to both sides of the Earth. And that's actually what B612 is working on, is that process. And one of the things that we realized is that it is absolutely critical when you're talking about asteroids hitting the Earth, that process be open and transparent, that others can understand, how did that calculation get done? Can I repeat it? Can I see what's behind the model? I mean, we see how important this is today with the pandemic, right? There's lots of models out there for what the progression of this disease will be, and they all have their various assumptions and so on. And it is very, very important that you show your work. Okay, that's what engenders public trust. And when you're talking about an asteroid hitting the Earth, you need public trust. Okay, you need to understand what's happening. So what's going to happen is that this cone is going to be shrinking in size, and at some point you're going to say, well, now I can't take it anymore. It's likely enough that we have to do something. Okay, same with you live in Houston, a hurricane's coming. At what point does the mayor of Houston say evacuate the city? Right? It's a probability that changes with time. And so at some point we may decide, for instance, to deflect an asteroid that's going to hit the Earth or has a very high chance of hitting the Earth. And you may have to make that decision before you know for sure that it's going to hit the Earth, right? Because maybe you don't have enough time. Now the deflection process, kind of simple, because when you have decades of notice, you only need to change the speed of an asteroid, and it is the speed that I'm talking about, going around the sun, by about a part in 10, 1 in 10 millionth. So in other words, if I look at the great speed at which these things are traveling around the sun, change the speed by about 1/100th of a mile an hour, almost nothing. And that's your job to make it. I mean, that tells you how precisely we can calculate orbits, is that we know the velocity accurate to within that in order to know whether it's going to hit the Earth, and because you're going to change it by that amount to make it miss the Earth. And that's as simple in most cases, simply hitting it with a small spacecraft. You just run into it. Okay. And now there are other things you can do for larger asteroids, but you just basically run into it with a small spacecraft. The simplest thing, you can do controlled things like what are known as gravity tractors. We can talk about that later, but just run into it with a small spacecraft. And in fact, we are testing out exactly that process in about 2 years. End of next year, a mission called DART is being launched. It's being built at Applied Physics Laboratory, but it's a NASA project. And they're going to change the orbit of a small asteroid about 4 times larger than the one that hit Tunguska, 4 times larger in size, so 100 times larger in mass, which is part of a binary system. It's 2 asteroids orbiting each other. We're going to change the orbit of the smaller one and measure, so we can measure exactly how much we've changed its orbit by. So it's something that we know how to do. It's relatively straightforward, but we're going to do it for the first time for real in about 1.5 years. Yeah. So watch out for that.
Yes, definitely. And that's DART stands for a double asteroid redirection test. So
exactly.
If people are interested in that, and I think that's out of Applied Physics Lab at Johns Hopkins, I believe.
That's right. And the launch is in October, I believe, of next year.
Yeah. So definitely just do a Google search for that on the NASA site, and you can read more about that. That maybe a question from Tim: do we have any asteroid deflection methods currently ready? I suppose that's the first. This is the first one, isn't it?
Yeah. So answer is yes, because that spacecraft is actually past its what's called critical design review. They're preparing it for many months ahead of time. It needs to be going through test, and then being mounted on the rocket. So that's happening here over the next months.
Yeah, and that's really cool. That's going to be very exciting.
But again, you shouldn't be thinking that we only have months to launch one of these things. We should know decades ahead of time. That's the kind of thing that you want. If you only have months, we're in big trouble.
Yeah, And that's where the detection comes in, and that's the role.
Years ahead of time.
Yeah.
Getting a good map of the solar system, understanding where they are and where they're going accurately enough so that we know precisely where they're going. That is the name of the game.
Yeah, that's cool. So we're coming up to the half-hour mark, and Ed, if you'd like to say a little bit more about the future of the B612, what are your plans? What are your hopes moving forward into the next decade?
Well, thanks. Yeah, we are, as I said, concentrating on those computational aspects of asteroid tracking. Now, there's going to be a lot of new observations and discoveries coming up because the Large Synoptic Survey Telescope is turning on again in about a year and a half, and that is going to increase the discovery rate of asteroids by more than a factor of 10. And that means we're going to have lots and lots and lots of new discoveries. Unfortunately, it also means many of those will not be well tracked to begin with because they will only have been tracked for a short period of time. And the longer you track an asteroid for, the better you can determine its orbit. So we're going to be faced with a lot of cases of asteroids in the coming years in which we know that they are going to come close to the Earth and that they do have a chance of hitting the Earth. And that's the best you will be able to say. And so we are working on the computational tools for understanding those situations. And we are working to make these computational tools available to researchers and usable by the world community, and making them open source and building the computational backend that can do this at scale. Again, LSST will observe something like 600,000 asteroids, both main belt and near Earth asteroid every night.
Yeah.
So that's a lot of number crunching you have to do. So you have to do this at scale. So this has become a giant computer science problem in some sense. And that's what we're working on.
Excellent. Well, if you want to know more about LSST, you want to know more about B612, you want to know more about Unistellar, we'll have those links put up. Obviously, you can use the old Google search to find those very, very easily. Ed, thank you very much for joining us today.
Thank you so much to SETI and for the great work that you guys do. I always have to give a shout out to you guys because you guys do wonderful work. So thank you for having me on.
And maybe speak to you again in a little while and see how things have turned out and things are going.
I look forward to that.
Okay. Take care, Ed. Bye-bye.
Take care. Bye-bye.
Bye-bye, everyone. Thanks for watching.